Good afternoon, everyone. Thank you for joining the Cognitive Systems Speaker Series call. Today, I'm happy to welcome and introduce Nathan Wilson. He's the Chief Technology Officer and co-founder of Nara. Nathan is a scientist and an entrepreneur focused on actualizing powerful new models of brain-based computation. After many years at MIT working on the mathematical logic of neural circuits, Nathan co-founded Nara, a Cambridge, Massachusetts artificial intelligence company developing synaptic intelligence that automatically finds and refines connections across data for recommendations and decisions within enterprises. Nathan holds many patents across artificial intelligence, and his research has been featured in top journals including Nature, Science, Proceedings of the National Academy of Sciences, Neuron, and the MIT Press. He's an enthusiastic writer and teacher and routinely appears in the popular press on current topics in artificial intelligence. Nathan now works to guide advancements at Nara as Chief Technology Officer. Nathan, thank you for being our presenter today, and I'm going to turn the call over to you.
Well, thank you so much, Diane, and it's really an honor to be here speaking at your series and with all of you here on the call today. Like you, I think we're very interested in that junction of where a couple fields are coming together. And, you know, we started out understanding the logic of neural networks, and then that has increasingly taken on a cognitive tone as applications have arisen that have been able to really start to span the gamut from how pieces of data get integrated into representations and then leveraged for actions and decisions. And so I'm really excited to be talking about cognition today from a couple different angles. So today, I really thought hard about what would be interesting for this group, and really thought it might be interesting because you're such an integrative group and interested in analogies and junctions that are arising, to focus on the junction between traditional neural networks and neuroscience. And what I mean by that is the field of neurobiology or neuroscience has historically taken one approach to understanding how neural networks work, and the so-called neural networks field has taken a slightly different approach, and they're starting to come together increasingly, and that's kind of an exciting time to be at, but really trying to understand how these things are shaping up and where the successful interplays could be. So I'm going to talk about the benefits of cross-pollination of fields like these, new learning rules and emerging analogies, so where the fields are starting to really say the same thing from different vantage points, and how we could use these as guides towards understanding cognitive processes. And finally, just mentioning a bit of our thinking on how recommendations and decision support can be a very effective domain for connecting neural networks and other learning systems to cognitive properties. So for many years, I've been working at the interface of neuroscience and computer science. I was at MIT for many years in a department called Brain and Cognitive Sciences. And before that, I actually majored in the first year that Cornell offered a cognitive studies program. And so cognitive has really been a focus, and like all of you, trying to find where are the subdisciplines that can connect for that. And so we're in the White Building, the Brain and Cog Complex at MIT, and across the street is the CSAIL, Computer Science and Artificial Intelligence Laboratory. And a lot of the people there spend a lot of their time just thinking, what is the analogy here between what the brain's doing and computation in general? And I think there's a lot of healthy and vigorous discussion and debate about is the human mind a good metaphor for what we're trying to build? Is it a good guide, or is it going to be something different? And I personally subscribe to the view that just like with airplanes, when we were first trying to understand flight, it's very fruitful to look to existing systems, just like they looked at birds, for understanding how we can build these sort of early systems that think the way we want them to. And I co-founded Nara, which is really creating applications. It's an AI company, one of the largest in Boston now, and increasingly the nation, really dedicated to building cognitive systems for companies. And so we've also learned a lot about, you know, how companies want to use cognitive systems and what's effective and what's not for interfacing with their systems. So I thought it would be fruitful to talk about kind of the stereotypes that keep fields apart, and many of the people on this call may be part of one of these fields. So, you know, by calling out the stereotypes, I mean no disrespect, and I've I have really good friends in both fields, and so I think it's safe to say how a lot of people stereotypically see each other. So I think a lot of deep learning or machine learning or AI people see neuroscientists as these kind of they can't see the big picture, right? They think we don't like the big picture. We're more interested in little pipettes and aliquots and ice, and for some reason just really rote redundant work, and they don't understand why this is, but that's sort of how they see the neuroscientist. And focus on insignificant details. Lots of interplay with rodents and monkeys and things like that for no apparent reason, and has trouble seeing the big picture compared to say machine learning researchers. That's the stereotype. And the stereotype goes both ways, I think, because I think neuroscientists see these insurgent neural network researchers as even though in reality they have many of the same goals, they see them as kind of this fun-loving, silly, frivolous, disconnected from reality group of people who have no grounding and hasn't paid any dues in the lab of arduous work, and they're disembodied from all the traditions, and they spend most of their time in coffee shops. And in reality, of course, deep learning researchers are contributing to one of the most important disciplines of the 21st century, as are all the people on this call. And so I think there's a lot of potential for experiment. Now that experimental tools are starting to work, and now that theory is starting to really acquire applied foci and a lot of frameworks, I think that there's a lot of opportunity for collaboration. So they really do share the same core orientation, right? So whether you call it an artificial neural network or you call it neurons in a circuit, the same goal really is understanding that general algorithm. And I think a lot of the people who work in the cognitive field are kind of intrigued that there could be frameworks or general principles that could work across domains. And I think a lot of these people think that the structure, they agree on the structure. It's a connectionist model. There's weights. It's not the same von Neumann architecture. It's about cultivating pathways and not necessarily hard coding the rules always, although it's not to say that pathways can't encode rules. And that really the weights are one of the key properties, and the intelligence and how you set the weights are very important. And this concept of structure is function, that if you can get the structure right, then the data that flows through it will beget the answer or the action or the behavior. And they face a lot of the same puzzles, which is what is the transfer function of a node? What is it trying to? How does it transform input to output? Is the representation localized to single neurons? Is it distributed across nodes, or is it a mix of the two? And then how are sequences learned? This is something that neuroscientists still haven't quite figured out, and neural network research is really focused on some exciting new models for this too. So same puzzle, same goal, and I think there's again more similarities than differences. So why, a starting point question is why would we turn to nature to even try to understand things like cognition? Can we just kind of do? Is it too much work or a waste of time? And I do think one of the the 20th century engineering feat, one of them along with computers was flight, and I think we did look pretty seriously at birds to do so. And a lot of people say you get these blogs, and half the bloggers say aviation came from birds, and even today airplanes look a lot like birds. And other people say, of course, today airplanes look nothing like birds, so it's kind of subjective, like with image recognition, right? But I'd say still, there are some physical similarities. I mean, you've got these wings and these little feet and this head with eyes and a tail, and there's some structural, but they're not completely divorced from each other. And I think obviously the Wright brothers spent a lot of time observing birds in flight as they were getting going, and so people on this call are like the Wright brothers of the 21st century, right? They're trying to they have these toy planes that they're trying to get off the ground for a little bit, and sometimes they coast for a while and it's very exciting, and we're at that exciting point where we're just trying to take off, and you feel that. And they were really inspired by Otto Lilienthal, who really is considered the founder of modern aviation, and he actually has spent the first part of his whole career understanding bird flight. He cataloged and wrote some of the best scientific work to understand bird flight, and I think that's how he was able to define the principles of lift and other things that the Wright brothers then drew from. So like Jan LeCun said last year, AI is to the brain as airplanes are to birds. The details are different, but the underlying principles are the same. And so I think as neuroscience starts to provide the tools to see inside the brain and understand the logic, we'll be able to use this to accelerate our cognitive systems. So neural networks is kind of, it goes up and down, and as everyone on the call knows, in its popularity. And shortly after we started the company, it started to get popular again, to our surprise. But they really are emerging as a dominant framework for machine learning, at least, and I think a lot of existing frameworks will get mapped to that. And then additionally, in neuroscience, they spent a century mapping, how do you take connectionist frameworks and map them to cognitive or psychological and social principles. And so all the layers of AI that people want to allegedly build next, which are, the cognitive layer or the psychological layer, the social layer, probably what people on this call are pioneering, this has already been partly mapped to connectionist models by neuroscientists who try to understand how, say, an emotion could intersect with a thought or a memory at the connection level. So maybe there's fruitful knowledge there that could then be taken further in some of the cognitive frameworks that you're building. So why now is now the right time, and timing is, of course, crucial with startups and with ideas. And I think neural networks finally has these rigorous frameworks and data sets for evaluating network intelligence, which simply weren't available just a few years ago. And the software, of course, exists now, too, for really isolating the key knobs that matter for the parameters of learning. And of course, the open source communities to start to dialogue about how to improve these parameters. Neuroscience has, I think, finally, it's really, there's a key moment that's going to happen in neuroscience, which is when you can do arbitrary input-output access to populations of cells that are behaving, and we contributed to that direction, and other people are too. But it's really being able to talk to cells at the network level, which has been elusive. We could always talk, observe big chunks of brains or single cells, and it's really when you can talk to and influence groups of cells that are computing something that we'll start to understand how they decide to connect to each other. And we're just about, I'd say in the 2010s and 2020s is when that's going to be achieved. So then we'll get those insights. What's interesting is different communities end up using different terms for things, but the principles can often be the same. So, what's the goal for each of these two fields of neuroscience and neural networks? Neuroscience, it's interesting that they talk a lot about the brain is trying as a goal to maximize reward. It's trying to maximize connections that lead to success. And neural networks actually make a goal of minimizing loss. So it's kind of this this psychological orientation of one's out of engineering, how do you make it more and more less imperfect, and the other is, well, how do you make the animal happy? And so there's that funny, but really the optimization functions are just the same thing upside down. But it's interesting that they chose that psychological orientation. What is the system doing to each of the fields? Well, neuroscience thinks that neural networks are built out of small micro successes. So when you associate two things that connote success, you're going to strengthen that association. And these micro successes somehow, in a bottom-up fashion, lead to organization and happy society at the network level. Neural networks, of course, take a more global view usually, which is there's a function you're trying to optimize, and we're going to globally work with the network to find the problems, find what parts of the network aren't contributing to this function very well, and backpropagate error in order to get them more in line. And so I think there is actually fundamental difference in how they see the network evolving, where neuroscience thinks there's lots of pairwise interactions and this kind of bottom-up learning, and I think neural networks thinks you start with a goal and then you build the network you train the network to match that goal at the global level. And then what are additional parameters for? Well, neuroscience says, well, there's lots of stuff layered onto learning rules, such as, and it's all about stabilizing firing rates. It's all about keeping things in the right dynamic range to maximize the information gain. And I think neural networks call that regularization, right? So it's really very, very similar concepts, but both to keep things in a certain range. And you can look at the sort of what the fields call rules as what's important for helping the system learn, and see if there's analogies there too. So, you know, a lot of the rules that we know about are historically constrained. So it's easy to measure brain activity going forward because it's electrical. So you can, you know, it's the loudest signal in the brain. Maybe the most important things that happen in the brain are not electrical at all. Maybe they're invisible electrically, but because they're loud and electrical, we measure feed-forward activity. There are signals that go backwards that could relate to something like backpropagation, but they tend to be invisible. And so one thing is, some people have actually done the bridge and said, well, if you have association like Hebbian learning, where two pairs of cells fire together and wire together, or spike timing dependent plasticity, where the timing of firing is important for determining who's out of sync, you could use these as error signals that would then propagate backwards. But then, you could look at the pair level mismatches as a local error signal, which could then be propagated backwards and backwards and backwards. And there are chemical signals that we know travel backwards across pathways. And that some are even released in proportion to how strong the synapse was. So if you have a synapse that was very active, but nevertheless erroneous, it could propagate more of these signals backwards. And there are vesicles that pick these up on the other side of the synapse and transport them up the axon through cytoplasmic transport to the nucleus, where they could then be passed backwards further. But eventually, with the type of genetic tags and other things, we'll be able to see these secret messages passing backwards and forwards through neurons, and that'll help us see the logic too. On the regularization side, you know, how do synapses resist the desire to go out of range? As you become successful and you become more powerful at driving the circuit, a lot of rules predict that you're just going to become more and more powerful and more successful. But the synapses resist this intentionally, and there are very well-described mechanisms where if you have chronically high levels of activity, they'll actually pull back receptors and pull back release to bring it back into range. And same if there's not enough activity, they'll add receptors to try to recover some signal. And so there's these very active and energy-intensive processes to keep every synapse in a certain range and keep the neuron that it lives on in a range. And so neurons really auto-tune, and they do this at different scales. There's synapses competing for these receptors and these resources, and so one will try to pull receptors away from another synapse. Within a neuron, in a network, the neuron itself is trying to maintain a range where it's not going to, you know, be too quiet and not fry itself from too much activity. And we and others have shown principles by which a neuron will either have lots of synapses that are very weak, or a few synapses that are very strong, almost like your friendships if you live in a big city or a small town. And finally, the whole network seems to have a set point where, as a group, it's trying to figure out how can we as a network be more active or less active. And principles like dropout, where you in neural network research, where you remove neurons during the training to try to help the network get more resilient. Dropout, neurons also undergo this, where a lot of the times most of the neurons are not firing. It's very sparse coding. They're very decorrelated, and it seems to be a property of the resilience that it can still compute and almost cogitate with very small sets of neurons involved and different sets at different times. And the synapses, of course, in the cognitive levels of the brain are incredibly unreliable compared to the muscle. The muscle synapses have to be incredibly reliable for you to walk, but at the cognitive level, for some reason, you get these 10% or less release rates where it gets the action potential, and 90% of the time it's just not going to, the synapse isn't going to transmit. And so why are they so almost intentionally unreliable? finally, I just want to call it a principle that I think is not used as much as it could be in neural networks, which is the idea of negative weights and inhibitory neurons. So, and we're starting to learn more about inhibition in the brain. You know, originally I think we all thought, okay, this is the part of the brain that tells you not to do things and it keeps you out of trouble. But people are starting to see that neurons love inhibition, and the brain spends an incredible amount of its energy on inhibition, which we didn't realize until we started recording without anesthesia. And we realized that almost most of the energy is spent turning things off. So why does it work so hard? Neurons are trying to maintain a balance. As they get more excitation, they add more inhibition to compensate. And these things are incredibly well matched. And the odd thing is the inhibition is most focused on the things the neuron cares about. So it's recruiting signals to turn itself off when it's processing what it cares about. It's very strange. And so that could be a rubric for understanding something about cognition, I think. There's an excitatory-inhibitory balance for every neuron at which it keeps itself on a knife edge of activation by maximizing its drive and its suppression going into it. Second, you know, we had a paper in Nature, and others have followed up on this, and it's a well-known principle that inhibition is not just turning things off or suppressing or silencing. It's actually scaling the whole dynamic of the local network, where somehow these inhibitory cells are able to take an average of how active the network is and in real time apply a scaling to make sure that the network doesn't go out of range or the cells stay in range, and it almost lets the network operate at many different levels of gain with the same network, so without losing the balance of the thought. So you can think of inhibition also as not just subtraction, but a division gain knob that scales the level of the network. And so looking at these, this is a confocal micrograph of cells connecting to each other, and there's magic in these cells that can teach us about the logic that was evolved to understand what cognition was really striving for. And this is especially true. I'll just take the last few minutes of the talk just to mention that we really see recommendations and decision support as a great cognitive problem and as a network learning problem. So just like games, I think DeepMind has done a really good job articulating that games cover the gamut from gathering data to representing state to making decisions, and it's a great model for this. We think enterprise decision support has these problems that require data and decisions, and how they connect one to the other. That is a great domain for understanding the properties of cognition. So you know, it connects perception to cognition and action. It remains a major commercial justification for machine learning, and it tends to have pretty highly structured data sets and goals and very codified arenas for success. So we really are trying to build networks that match immediate context to appropriate decisions. So for travel, which spot should I visit when my plane lands? You know, matching, if I understand things about what movies you like, that's a matching problem too. What movie would be best for you or your friends? How would you match the doctor to a patient with an immediate medical context? On crime or intelligence side, which events could be related to this incident? If the incident has these contextual properties, what other events are similar to that? And fraud, is there a deviation between someone's profile and what they're currently doing as an action? And then fault tolerance, you know, in the supply chain, how do you take a snapshot of a factory or a supply chain and say, you know, these components are predictive of this state happening? So we're really trying to take a knowledge-based approach to this. We think knowledge in addition to optimization is crucial, and that's where we really appreciate, you know, the deep work of IBM and other cognitive groups that are really trying to understand the representation of knowledge, because we don't think it's just going to be about black box optimization. But it's really building networks that have explicit representations for understanding, you know, what is related, what is similar, and then using that to then bridge cues that you see to decisions and actions. So I'll just leave you with one visual before I close, but it's that you can build these networks for any domain that, again, link primary data to suggested actions. And as a toy example of this, I'll just show you one of the networks we built where we analyzed the universe of movies. And we've built a network now that doesn't just have the movies in it and the statistical learning of people who watch this also watch this, but we embed in that the fine-grained attributes learned from structured and unstructured data that define these movies, that this is a detective movie, that this has elements of romance, that this has an underlying theme of death or dark. And these concepts, these nodal concepts, can form bridges between movies that weren't otherwise there. So that if you come in and you say, I like this movie, and I feel like something playful tonight, it can plug those into the network and it will activate other places in the network through excitation and inhibition, and through these themes that have been connected to light up new opportunities for movies you can decide to act on. And this framework of deciding action from primary data, I think, is very powerful and replicable, and we've now applied it to many different domains, including intelligence and travel and the fraud and supply chain case we talked about. And so we're trying to understand, and you guys can help us with this, but just how cognitive principles can be expressed as a network function that maps primary data to decisions. So with that, I'll turn it over to questions, but I just thank you again for your time, and I hope this was a little bit stimulating to think, where is neuroscience at? How does it relate to current neural networks, and how can both these come together to then give rise to more interesting cognitive questions and applications? So thank you for your time.
Thank you, Nathan. This was fascinating. We have just a couple of minutes for questions, so audience, press *1 to unmute your line, and please ask questions.
Hi, Nathan. This is Jim Spora. Thanks for a very stimulating presentation. I'm wondering, for that last thing that you showed, how many different movies did you have represented in that cloud, and was it based on analyzing the actual video or just abstract textual representations of the movies?
Good question. The movies were gathered from multiple data sets on the internet that we then fused and standardized. And so there were about, I think, 40,000 movies in that graph, mainly American movies. And to your other question, we did not do any image or video analysis. We did rely on data sources that had done those analyses and the metadata that they extracted. And so but a lot of our analysis was unstructured text and structured data from internet sources.
Okay. Yeah, I recently saw something on the web where one research group was trying to predict, when things would happen in various television shows and movies, and including, like when people would kiss, and they were doing video analysis. I'm not sure if you saw that or not.
Oh, right, when they would high five and such. Yeah, that was impressive. Yeah.
Thank you. Thank you.
Thank you.
Other questions for Nathan?
Thank you, Nathan. This is Scott McLeod. Fascinating. I'm curious how you would trace each of all 7,943 languages back to the cellular and the nano or atomic levels even. You mentioned one rubric. Are there ways that accessing how the words get expressed in all these languages might touch on even at the nano level?
Oh, wow, that's a great question. We're only just starting to do multi-language ourselves, and I know they're real experts on this call. But my bias is we would try to make real language agnostic concepts at a core of the network, and then map. And this wouldn't be perfect, but it would map language transforms of concepts in other languages onto those core concepts that could then interact. So there would almost be a translation layer into the core network, and then the core network would have these concepts that, even though people see things differently, they may be good enough to at least get started trying to map many domains together. So really keeping the translation peripheral to the core, almost like human-level construct of knowledge. But I agree that ideally different languages thought and language approach things so differently that it may be fruitful to have different networks for different languages too, or groups of languages. Great.
Fascinating. Hope to be in touch later about this. Thank you.
Thanks.
Thanks, Scott. and thanks, Nathan. We're out of time, but I captured some questions that came into the chat that you didn't see, Nathan, because you were presenting, and I'll send those along to you. And I encourage others on the line to ask further questions of Nathan in our LinkedIn discussion group. I'll be putting a post out about this talk. Nathan, thank you very much for taking the time and for giving us a great presentation, and we'll look forward to seeing everybody the next time.
Oh, thank you, and anytime, and I'll look forward to the questions. Appreciate it.
Thanks, Nathan. Bye, everybody. Have a good day.
Bye.